Ok, mi sentite?
Sì.
Va bene, allora ci presentiamo in italiano e poi passiamo in inglese come introduzione. Prima di tutto scusatemi per ieri perché non sono riuscito a vi chiederei pure se è possibile qualcuno di voi di attivare la telecamera, così per me diventa più facile l'interazione. Vabbè, ma vediamo un attimo come riusciamo a organizzarci. Sebastian Restrepo Hernandez.
Hello, Professor.
Okay, so you speak English.
Yes, sir.
So, no Italian. Okay. You first of all, are you coming from where? What is your...
From Colombia.
So, okay, you are from Colombia. Okay. And then you are enrolled here for the full master or only for this course?
On the full master.
Full master. Okay, very good. So, welcome.
Thank you.
So, do you understand Italian or?
No, sir. I don't speak Italian, but it's very similar to the Spanish, so I can understand some words.
Okay. So I have to find the syllabus in English. It should be available somewhere in my directory. So just 1 minute. First of all, do you see my screen? Okay.
Yes, sir.
Okay, very good. So you and your colleagues, of course. Yeah, here we go. So, okay, this was the web page of the course, and there should be also the English version, I imagine. Yeah, that should be here. Yeah, and yeah, okay. So here you find the objectives and the main information on the content. Okay. Well, we will not go through all text and description. We just focus on the objective of the courses. First of all, as you may imagine, this is as you know, this is the first year for this course, and for me it's the first time, of course, with this kind of course with in a particular master, because as you know, this is a very broad, has very broad objectives and topics, and is mostly oriented to industrial applications. Actually, the name is contains the word smart industry, which means that you will be at the end of your master, you will be a smart engineer. But this is just to recall that the term smartness, at least for the smartness of this course, is in first of all horizontal capabilities that should be given to the students, and particularly this is related to the fact that this master is open to students that they already have a bachelor in mechanical engineering, in management engineering, in chemical engineering and electronic engineering. So which means the entire the broad spectrum of an industrial engineer could found in the industry. And our course, I'm not alone in this course, which is 9 credits. I will teach this course together with the Professor Carlo Renno, who will attend in the second half of the semester. I will give you my topics will be dealt in for 4 credits, whereas the topics of Professor Renno will cover 5 credits. Overall, there are 9 credits, 90 hours. Although, if you see at the time schedule, we will have a little bit more than these hours. This will help in recovering some, classes that perhaps they may will be cancelled because of holidays or problems like this. For instance, the one yesterday, I apologize for yesterday. I was obliged to attend an official meeting, so I could not start the course yesterday. So just to explain you what was our objective when we wrote this syllabus, and the name of the course, first of all, is, you see here, is Optimization and Management of Energy Systems. Myself and Professor Renno, we are in Italian we say thermal engineer. I mean, we are working in the area of thermodynamics. Professor Renno is working on the basics, and I'm more on applied thermodynamics in the way that I'm dealing with all topics that are related to energy conversion. And before going ahead with focusing better on the topics, I would like to know what is your what is your bachelor. Let's start from Mr. Terracciano. What was your first level course? Mechanical
engineering.
Okay, so you are a mechanical engineer, and
yes, from Fiscia.
From University of Salerno. Mr. Adinolfi?
Yes, I'm also a mechanical engineer from this university.
Very good. Mr. Hernandez?
I'm also a mechanical engineer.
Okay, very good. Mrs. Faustini? Miss Faustini? Okay, do you know the other colleague, Roberto Mele, whether he's mechanical, management, electronic?
Management.
Is management. Okay, so this is a good starting point, at least for me, because as you will see in the program, in the syllabus, we introduced some we reported some topics that you already know. So I imagine also Mr. Hernandez will not be difficult to follow our reasoning when we speak on gas turbine or steam plants. Did you study steam plants, gas turbines, internal combustion engine?
Yes, sir.
So you know. Well, this is a good point, because this will not require too much introduction and particular information to be given, because you already know what is our main topic. So let's go ahead with the objective of the course. The objectives are as reported here. Hope you can read. Is large enough?
Yes.
Okay. So as reported here, the aim of this course, which is called Optimization, the title is Optimization and Management of Energy System, is to provide knowledge on energy systems, but with the objective of optimizing and managing the energy conversion systems, the most important one. And we have two modules, as I already introduced. So from my side, I will introduce some concepts of modeling. So we will start with the modeling, because if you want to be smart engineer, you should know all computational tools that may help you in becoming smarter than other engineers, of course. I'm not kidding, of course, but it may appear a joke. It's not a joke, because if you want to optimize and manage an energy system that you could find in any industrial plant, for example, or you want to design any energy system, like could be, for example, hybrid propulsion system, like the one we have now on new cars, that they have together batteries and conventional engine. You must know the problem of the optimization and the management. Although they could be considered independently, optimization and management, because optimization means that you are trying to design, build, and conceptualize a system which is optimized. Optimized means that you are not losing any, in our case, for example, any energy. Optimization is also a scheduling, of course, of a process that is optimized. The optimization refers basically to, for example, to the fact that you are allocating the resources, also for production, for example, of your system that you designed. And management is something that could be also related to optimization, and we'll see in a minute. And management means that is, of course, you want to run, let's say, the system in a best way, or you want to make sure that your system, when it's running, is following what are your objectives. Whether objectives are optimized or not, for example, when you are driving a car, you are managing the car in a way that management includes the concept of control, of course. So the control in mechanical engineering, we mostly split management and control, because control is something related to the device. So the device, you ask to your device, any device, to perform in some way, to do something, and then you control the system, because the system reacts in some way with respect to your input. Well, management is more broad sense term. It covers everything, which includes also the control. For example, let me provide you with an example that is very familiar to me. It's for a car. For example, when you're driving a car, you are controlling the car, because you are controlling the steers, you are the steer wheel, in order to have to move on right or left. You are controlling, for example, the pedal for the acceleration or for braking, and this is main control functions. But your car has to be managed in some way, and management is something related, for example, to the concept of checking periodically the oil in your engine, and you are managing the system in such a way that he could perform at the best of its performance, And when you put together control and management, of course, you are the system that is working at the best. But does not mean that it is optimized, for example. Because you, for example, you can drive the car on a straight line, and I will try now to give you an example. Suppose that is your curvature, and then your trajectory is this one, supposed to be the medium trajectory. And then when you are driving, you could drive either in this way, following this line, or you can drive. Can you understand the different colors? Okay. Yeah. Okay. And then on the other end, you are driving this way. Of course, you are controlling the steering wheel of your car with this brown trajectory, which keeps you in the line here because you want to stay within the road, because if you go out, you may damage your car, you may procure, you may have some injuries to yourself or to other people moving with you. So if you are following the blue, if you are following the brown one, so the one, this most wavy one, which is this one, okay, you are still keeping your car within the road, and so you are controlling your car, so you are within the road, within the objectives of your problem. So keep the car running on that road. Whereas if you are following the blue one, okay, this is okay in objective, let's say within the objective, although the main objective is this one, okay, I will say is a fair achievement of your objective. Here, this is the objective for your system. If you are here, you are sure that you are following your objective. This is the objective achieved. So here you achieve an objective which is not the main objective, or is not compliant with the starting objective, which is the optimized one. Why we say optimized? Because this is, for example, the shortest way you may you should follow in order to reduce, for example, the fuel consumption, because the length of the brown trajectory is higher than the length of the blue one, or of course the red one. Perhaps you may drive and then you reduce the consumption. You will drive faster because, of course, in order to keep, your trajectory in the brown one, for example, you need to continuously steer your car, and the velocity, of course, you may understand this is not the same you may have with a line, a continuous line in like the blue one. So these are two examples of control, for example. Okay, so this is the problem of controlling the car. For example, and during your trajectory, for example, you can brake, or you can change, for example, you can brake, as I said before. You can change the gear of your car unless it's an automatic gear system or whatever. Well, if this is a way of controlling the car, and this is a fair achievement of your objective, and this is the objective you had, and then you may optimize your system if you are controlling the car in such a way to reduce, for example, the consumption. Suppose you may suppose that this is the elevation of your trajectory. For example, this is H, and this is, suppose this is S, your trajectory, that is this one. Okay, you know that if your car, which is this one, not very nice, has a certain mass m, and then you can, for this problem, you know, as an engineer, you must analyze the problem, and then you must reach the synthesis and then the solution. So your mass, this is the mass of your car. You want certain velocity, and then you may, for example, here control the system in such a way that you don't brake, you don't accelerate, in order to get benefit of the gravitational forces that let your system running a certain velocity, whereas when you are here, you have a certain velocity going uphill, or here downhill and uphill and whatever. So you are controlling your car, accelerating, braking, or whatever. But if you want to reduce your fuel consumption, for example, you must optimize this. There are studies, even in my group, we are performing such kind of activity. And then you must identify what should be the best velocity when you move downhill, for example here, okay, or uphill when you are moving in this direction. So these are two examples of how to control your car. You are controlling in a fair way because you, as human being, you are clever enough to understand that the Brown trajectory is not the best. But when you are moving, but you are controlling the car in a heuristic manner. But if you want to achieve your optimization, which means reducing the fuel consumption, over here is not immediately achievable the optimal trajectory in terms of velocity in space as a function of space. Of course, you cannot achieve these by heuristic approach. So you know that in the downhill you should release the pedal of acceleration, or eventually put your feet on the braking pedal, and you know on the other end that on uphill you should accelerate and avoid to use the braking system. But it will be something empirically from heuristic consideration. But if you want to achieve the optimal solution to this problem, you must perform an optimization problem. So you must solve an optimization problem, which will be I don't know whether, yeah. Well, I was, okay. An optimization problem that will be formalized in this way. Minimize the m.f is the fuel mass flow rate of your engine, of your propulsion system. If it's an electrical car, there is no problem. This will be something related to the power, because as you may remember, the power that you spend in this system is, of course, is related to the power you spend along this trajectory from 0. Okay, I have to move 0 to, let's say, S, and this is S, the coordinate. So if we move ahead, you may remember, but perhaps I'm going too much ahead, but this is an introduction, of course. So the power you are using for your car in a certain point of your you have a certain power here. In a certain point, which is the mass flow rate in this point times the overheating value times the efficiency of your system. I may imagine that you all remember this formula, okay, which is the power generated by the engine, for example, and used for the propulsion of this vehicle along this trajectory. So we don't go too much into the detail of this. Please just explain me whether this is okay. And this is the propulsion power. But the propulsion power could be, let's call it P. Yeah. PP, which is propulsion power, which could be either from engine, from an electric motor, okay? And then you may, in order to minimize the energy consumption, your energy propulsion is the integral or propulsion power in time. Okay. Of course, you can write this as a function of space. It's just a change of variable, reminding that v is ds over dt, and then you may use this in order to change your variable, your system, of course. Okay. So you may substitute delta t with the des over v. This will be in space instead of time. So let's go back to the original problem we were analyzing. This one. So your problem will be minimized. Okay, it is clear that your let's say this is thermal power or chemical power or whatever. This is electrical power, and then your thermal power is instantaneous value fuel times HI then eta G. Or be careful, because P thermal or P traction should account for within global efficiency. We included also engine plus transmission. Okay, is that clear to you? Please let me check whether you are following my reasoning.
Yes, clear.
Okay, so just to, if you have a car, you have, this is the engine, internal combustion engine, then you have the gearbox, then you have the transmission, you know, this is the differential, okay, and then at this level you have some fuel flow rate, and then here you generate some mechanical power, and here you have P traction, okay, and along this line you have dissipation, mechanical dissipation in the gearbox, for example, or in differential, or whatever it is. And then this mechanical power is needed in order to balance all the power which is required in order to move your car at certain velocity. And then if you see your car, okay, the car has velocity v and a certain force F, and then the overall, and then you have this is motive force, let's say, and this is the resistance force. Okay, so then the power for traction should be equal the power, resistance power, which is FR times V. Okay, this is a power which is as a negative sign compared to the other. So let's come back to this problem. Sorry. Okay, I should learn. Okay, that's nice. Yeah. So let's come back to this to this problem, and then yeah. So our problem is to minimize this fuel consumption. In order to do that in an analytical way, you must have you must know your system, and then you must build a model which gives you the from this relationship. For example, okay, you have the dynamic the equation of dynamics, which is this is mass of the vehicle, the V over Okay, so you know this. When you are in equilibrium, you don't have any acceleration. This is the mass of the vehicle. This is the, here we have the velocity and the traction force and resistance force. So this is your equation. And in order to, the resistance forces are related to, for example, aerodynamic drag, or aerodynamic drag. You have the friction of the wheel and the road. Okay. You have all problems related to the resistances, basically, that are the friction interaction between the wheel and the road and the aerodynamic. And here, your traction force is something related to the torque that is produced by your engine, or let's generated by the engine, with all the efficiency of transmission and so on. So I'm not analytically precise, of course, in this description, but it's just to explain you how it works. So then, this is the motive force, which is a function which is related to the torque, and the torque of the engine is a function, of course, of omega, which is engine speed, and other control variable. And basically this is defined in terms of x and u, where x are called the state variables and u are control variables. So if we start from here, how we minimize the fuel? We minimize the fuel by controlling your system. Controlling your system, which is either a problem of controlling, for example, as we said here, the steer and accelerator and the brake, and this is a macroscopic control like the one we are doing here. The control variable, this problem here, is the velocity, and then implicitly is the control of the pedal, of accelerator, and the brake. Whereas the optimization of control is also related to the parameters of controlling your engine. For example, the air-fuel ratio. You know what is air-fuel ratio? Air-fuel ratio is the ratio between air and fuel that you inject in your engine. So the control can be considered on two scales. One scale is the big one, is a macroscopic scale here, and then we control the velocity by acting on the pedal and on the brake. But you can control also the engine here. Okay, so you may have U engine, which is the control variable, and then you may have also U, let's say, vehicle. So you have two U control variables. Of course, in order to simplify the problem, we consider as control variable of this problem only the macroscopic variable. So u is the velocity. And then you would like to find the optimal velocity as a function of time. So you minimize your fuel consumption by controlling the u variable with certain limits that are, for example, that V max should be always less than velocity limits that are imposed by the rules, by the road, and so on. But you may have also other control variable, but I don't want to go too much into the detail. So this problem is a so-called a constrained minimization problem, because you have the minimization problem and then you have some constraints on here. So this is a way to have a sort of optimal management of your system. The objective of this course will be to provide you with some analytical instruments, tools, in order to be able to approach the optimization of your problem. We will see an example for us it will be the first one. You may remember when we talk about a pump, which is a typical industrial problem, you have the load, the head, or here, H. In Italian, we call it prevalenza, and Q dot is the flow rate of the water in your pump. So suppose that you have a scheme like this. This is your pump, and then this is your this could be a valve, for example. We remember that we have an internal characteristic here. We call it. This is the an external one. Okay, this is the useful head, and these are the losses in the duct. Okay, and this HU is in the specific case is this head in meters. Your problem, what is your problem? Your problem may be, for example, that you want to know, suppose that you have, and this is the case, several curves representing, for example, the performance of your pump as a function of speed we call n. Okay, we know that on this curve we have some no, it's too light. And we know that, are you able to see this?
Yes.
What are those? These ellipses. Each ellipse of this is something related to the efficiency. I don't know whether I'm too fast or and efficiency of your pump is something that goes in this way. So you have the maximum efficiency here, okay? And then you have the minimum efficiency on the side. What is your problem? Your problem is the following. Since your pump has an electric machine that takes the electric energy from the line, there's certain power here, which is the mass flow rate times we call it Euler work. I don't know whether, I mean, for sure those who have who hold the bachelor degree from University of Salerno, they know exactly what I'm talking about. I don't know whether Mr. Hernandez is following me in terms of names and definitions, but this is the power, which is the mass flow rate within the pump times the Euler work, as we call it, divided by the efficiency of the pump. Okay, and then if I want to minimize the power, I should find on this system a working point, which should be, for example, here. This means that I will be the minimum fuel consumption. But if I'm obliged to have a certain flow rate, for example, I must identify the best working place here with the efficiency. And then I will move in terms of, for example, of the dimensions, okay? Dimensioning, I mean, setting the dimensions of my problem, the size of my problem. I may use an optimization problem where I will minimize the fuel because I'm going to select, for example, the right pump or whatever will be any control variable. And then we will see this. How we will do this? Of course, and this is one point. I don't know whether on this, what I've said so far is critical, you don't understand, or I was not clear. Please tell me, and then I will get back to these explanations that was objective, was to introduce the concept of control and management and optimization. I hope this, although it was broad, it was fair enough to be understandable, at the same time you got the message. Please tell me. No, so there is no problem. So the aim of this course is, as we said, is to provide you with the main knowledge to optimize and manage the main energy conversion systems. So we'll deal with operating machines, power plants. Here are just mentioned steam and gas turbine and reciprocating engine. We will be, flexible with this course because we can consider that all of you understand what is an internal combustion engine or a gas turbine. Then we will speak about renewable energy for power generation. And this will be also used by Professor Reno in the second half of the course for example, for solar energy. And then we will work, as shown here, some steam compression and absorption refrigeration machines, photovoltaic system and hybrid photovoltaic system and concentrated. I will provide you with some input at this level, and then I will go more on wind energy for what concerns the renewables. So if you read this ability to apply knowledge and understanding, you will see that at the end of the course you should be able to analyze the energy systems, basically the energy flows in either conventional or renewable systems. I will provide you with some quantitative tools. Basically, we will not use MATLAB, which would have been the best way, but we will rely more on Excel. I will show you how to optimize a problem in Excel. We will do the example of the pump as a reference, and perhaps we will be able also to do something else before closing this my part. And then we will I will spend quite some time on the methodology, which are not explicitly reported here, but if you want to exploit in optimal way energy resources or things like that, you should understand the problem of mathematical modeling, because as we have seen here, is a mathematical problem. So you see how a simple problem, a problem of everyday life, driving, we can transform this problem in a mathematical problem. So this is the path that any engineer, any modern engineer, any smart engineer should follow in professional work. Is that clear? And here, for example, if you want to optimize, you must have the mathematical representation, for example, of the efficiency, mathematical representation of your external characteristic, as we call it in Italian, or the internal characteristics. You should know all this information. For example, the relationship between, as we said before, the flow rate with the external characteristics. We know that if we reduce, for example, the section, so we close the valve, we have an increase in the characteristic which has this way. If we have a straight line instead of having these curves here and here, and then we put here, most likely we will have a line like this. If we move down the second reservoir, we will move in this direction. So all those things should be should be represented in a mathematical way in order to minimize to optimize your problem in order to minimize the energy consumption in a certain interval time, which could be from 0 and t, but E from 0 and t can be written as integral from 0 to t of p in dt, okay? Which is, of course, a function of these variables, each function of time, okay? So let's move now to, there are some information. Here is a detail of the contents. I'm sure you have seen it. Of course, as decisions taken by the school, it has decided this course will be given in the virtual room, so will be not given in a class. I'm very sorry for this, and I'm really disappointing. Just let me give you this my message, because I don't like this kind of approach, because I don't see you, I don't have any feedback. I understand for those who are not foreigner Italians, they are obliged to listen to me in English, but this is could be a good opportunity, provided I will be able to speak good English, and this is not the case because I'm not a native English, but I hope that you understand, and hope you and I ask you to stop me, to ask to repeat sentences and words in cases I will not be clear enough. I don't know how is so far. Are you okay so far? Are there any limits that you want to report to me? You believe that I'm not clear or you don't understand? Just stop me and tell me now whether there are problems. Don't be shy.
For me, it's okay. I don't know what my classmates will think about it.
Yeah, well, I did not expect a complaint from your side, because I'm supposed that if you are from another country, you already arranged in such a way to be more familiar with the English. But I was mainly directing this message to the Italian students. But so if there are problems, please, thank you anyway for your comments. Okay, very good. And here is exam. I know that you, as a student, you want to know from the beginning how the exam is performed. There will be a check that could be either something written, but just in front of me, or oral description. It depends on the timing, but there is nothing special. We will not go for hours of written exam. We will try to understand exactly how we are reasoning on the topic. we will check the capabilities you have in solving a typical design or management problem of energy conversion plant for industrial or civil applications. This is typical, for example, industrial problem, but also a civil engineering problem, because if this is the pump for heating system, the main difference is that you have also, suppose that here you have the heat exchangers in each room, and then you are a return, and this will change the head, but this will be analyzed in the rest. Okay, so I want to ask you whether it is okay with you so far, whether you are okay, just the courses. These are the main courses, the main books and texts, but what we suggest you to use our slides. I will provide you with the slides for my part, and of course, try to follow the books. I will provide you with the information. Basically, they are not so far from those we used at first level courses. This is, for example, a book, an Italian one, but I will provide you with the text in English time by time. I mean, this was just to provide you with some information. First of all, before closing this introduction, I want to apologize in advance if you will not find something completely strictly consistent with this description of the course. So we will move a little bit around because, for example, this is not the case of this year. Some colleagues of next year's, for example, they may come from electronic engineering, or from chemical engineering, and then not the case of this year. We must accommodate to give some space to more basics, whereas in this year you are almost coming from mechanical and management engineering, so most of the concepts have been already given during the bachelor course. Okay, so apologize if I will not follow strictly this path, but this is a way to provide you with more information to better apply your knowledge. Is that right? Do you understand this? Do you agree with this?
Yes, it's a good idea.
Okay, so we will try. That's why, for example, this year, for sure, I will provide you with more mathematical modeling, so which provides to more smartness, let's say, to your background. So now we stop, and then we resume in 5-10 minutes, and then we stop at 11. Since we are obliged to have hours of 50 minutes, I will not stop two times when we are 3 hours, but I will stop only once. I'm usually I'm trying to be precise in time with the beginning of the class, although I understand that they are at 8:30 on Tuesday, on Wednesday, and in afternoon on Friday. But I will show up if there is a problem. I will try to send you a message through Teams. So please forgive me if I will not be precise in some occasions, but I'm usually in time. So we will start at around 8:35, 8:40, the latest, and then we will have one break at around 10, and then we close at 11 precisely. You will not be late because of the class will not finish in time. Okay, so let's stop here for a few minutes, and then we resume and we start with the introduction to mathematical modeling. Okay?
Okay.
Thank you.
Okay.
Thank you.